Good afternoon. Have your lunch. Don't worry about this. Right. So what we're going to do, we're going to continue on the problem that we have. So what it states down here is that buckling, the question says that it prevents buckling in the YY axis. So now what we're going to find, we are going to determine our Y max, and also we would like to determine the maximum stress. Now, given that the Young's modulus of steel, so this is a steel column, we are using at 200 times 10 to the power 9 Pascal, and also given that we have a yield stress of 360 times 10 to the power 6 Pascal. So these are information that are given. So the formula that we are going to use, and this formula will be provided, is we are going to use stress max. So formula, or before we go on, we know that this is classified as eccentric buckling. Analysis. So we have stress max is equal to P over A. And then we have 1 plus by EC over R squared. Then we have secant pi over 2. And we have square root of P over PCR. So this is one form. And note that PCR will be equal to pi squared EI over the equivalent length. So this is a, so sorry, let me call this L. Okay. And this L is dependent on the fixturing. So i.e., is it free or is it pin or is it fixed? So you have 3 different combinations. So we are then the next formula. So all this that, by the way, by Thursday I will post the formula sheet for term test 1. A good news for you is term test 1, we're only going to focus on what? Buckling. Are we clear? So do all the questions in buckling and you'll be fine. Are we clear? And also look at the examples that what I've done, okay? So this will be provided. And this will be provided. Okay. And then the other formula that we're going to use, we're going to find out what is Y max is equal to E secant square root, another bracket, sorry, P over EI and L over 2 and then minus 1. Okay. So I'm going to get this image across. And before, at the class held at 10:30, we know that this is our rotation about X. We know that the buckling will occur in this way. Okay, we know the buckling will occur this way. And I draw this, I deliberately draw this straight because this is fixed. And the other end, as is mentioned in the question at the top, it is pinned. Okay. So one end fixed, one end pinned. A table will be provided, and this table will have this sort of information. Where is it? I just give you a preview of what the formula sheet will have, okay? Not here. Maybe was it week 1? Hold on, I beg your pardon. Where is the one that I have ordered? Oh, no, not here. Oh, really? I think it's in week 2, where I have all the diagrams of, hold on. Nope. My bad. Still looking. Nope. Hey, is it? Where I had all the last Tuesday? So week 3 Tuesday. Thank you. Yeah. Muchas gracias. So these figures will be provided. You don't need to memorize this because I can't. Okay, so you know that one side is pinned, one side is fixed. So from here, we know that our LE is equal to 0.7 L. Okay. So from here, more important is I want you all to focus on the diagram. So what we are going to do now is which second moment of area we're going to take. Are we going to take IXX, or I'm going to ask you a question? This is where the analysis will come in. Which second moment of area to take? Is it IXX or IYY? Okay, so which one will you take? Anyone? Yes. Why? Why is it IXX? IXX is correct. Yes. Yeah, so that's why I draw this. Oi, you have to follow what I do, okay, to the very dot. Okay, that is easy. Or not, you go bananas. When you go bananas, I go bananas. Can you look at the curvature? Okay, the curvature of the deformation and the curvature of what? Of Rx are the same curvature, yes or no? When that's the case, we are going to select what? I've taught this course 10 times now. Always students make this common mistake. Okay, don't. Okay, listen to me and do the analysis. When that's the case, right, we can determine that this will be our what? Width. Why that is our width? Because the axis of interest is which one? XX. Yes or no? And then if that's the case, this direction will be the what? Will be the depth. Okay. Now, the next question is why we have to determine Ixx or Iyy. Okay, if you look at the formula, you have a what? You have a R squared, right? So R squared, we know that I is equal to what? AR squared, yes or no? With this, we have to determine what is our what? What is our I first? Are we clear? Okay. So from here, we are going to determine Ixx. I'm going to sketch this out. So there are a lot of ways that you can determine Ixx. Okay, this is just one way. So this is the axis of interest. So this is our XX. As I drew earlier, this will be known as our width. Over here will be known as our depth. Okay. So some geometry information. We know from here to here, this is 120 millimeters. From here to here, this is 100 millimeters. Distance from here to here is 10 millimeters. And distance from here to here is 10 millimeters. Likewise, distance from here to here is 10 millimeters. Okay, so we want to find Ixx. So what we are going to, there are different ways of doing it. So Ixx is equal to, so the width is 100. The depth is 120. Power of 3 divided by 12. So this represents the entire rectangle. Okay. So what I'm going to do is I'm going to minus up. I'm going to take away the top and the bottom portion. Okay. I'm going to remove the top and the bottom portion. Okay. So this is minus 2 because there's a top and a bottom. The width will be 45 and the depth will be 100 cubed over 12. Okay. So this will be equal to 100 times by 120 power of 3 divided by 12 minus by 45 times by 100 power of 3 divided by 12 times 2. So it's equal to 6.9 times 10 to the power minus 6 or times 10 to the power 6 millimeter 4, or is equal to 6.9 times 10 to the power 6 meter 4. Is this okay for you? How I get second moment of area? Are we clear? There's a different method, okay, that you can also do. You want me to do the other method, or this is okay? This is good. Okay, so we found our second moment of area. So the next thing that we do, we're going to determine the radius of gyration about the x-axis. So from here, we know that Rx is equal to Ix over A. Okay. So our cross-sectional area, okay, let's determine our cross-sectional area first. So it's equal to 120, or yeah, let's do 100 multiplied by 120 minus by twice 45 multiplied by 100. Okay. So all this is in millimeters. It's equal to 3,000, or 3 times 10 to the power 3 millimeter squared. So change to meter. Wait, 3. Yep. So this will be equal to 3 times 10 to the power minus 3 meter squared. Okay. So from here, therefore,